Here we go. Okay, good afternoon. Keep on saying good morning. Probably I'm starting the day off. Good afternoon, students. Welcome to Lectures 2. We are starting with chapter 9, which is 3-phase. And like I said, we're definitely going a chapter a week. Yeah, that's basically the nature of the subject. So yeah, 3-phase, page 9.1. If you have a textbook, and yeah, that should obviously. Furthermore, chapter 19, if you're using John Bird, our secondary textbook for more examples as well, I'd recommend obviously referring to that chapter as well. Okay, so where we are currently moving, yeah, seems like I thought this lecture would be on campus for whatever reason, but not. Possibly it's a good thing, especially due to this load shedding business, which is no problem. But the good news from what I can see here, well, obviously, we have 2 more chapters after this, and all I can tell you is that the subsequent chapters are quite easy, and you'll be done by the 4th of May with no more elective content. So we've just got to go fast for 2 weeks. And what's nice about the next 2 chapters, I think they're a lot more easy. They're a lot easier than the other. In fact, electives is easy as a whole. But I mean, we have that. The only concern I have obviously is moms, because moms, yeah, it's something is it's a bit rough there in terms of time, and I somehow need to probably get a lecture in. I'm like, I'd say 2 lectures behind arguably, so I need to make a plan, and I'll discuss that with you on Friday obviously. So the only thing is our next lecture won't be on Wednesday next week. It'll be on Friday because of the public holiday. And we'll have it from 12 till 3. In fact, it could even be less. I'd actually possibly even like to squeeze in transformers as well. 12, so I wouldn't say 15:30. And if I could squeeze in transformers here, it would be fantastic. Yeah. But I typically keep it because it's the concepts only like one concept, and it's introduced with transformers is kind of like 2. But the stuff is very, 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 very manageable. So yeah, that's our plan for this. And then before we start, I'd like to just open the floor, like I said, at 5 or 10 minutes for the assignment. First of all, I've received 2 groups only, and I haven't got any groups from other students. So it's a bit concerning for me. I think fun enough, just most of the students actually decided to have groups a year, whereas I think around 2 students, 3 students have not decided on a group. So can we just get some feedback on the assignment? How are you finding the assignments? Where are you now? Any tips for your fellow students, etc., etc. Mr. Breed can start, and then anyone else can just follow. Thank you.
For myself, sir, the only thing was the frequency. I spent a lot of time trying to work that one out.
No, but you shouldn't have worked it out, but I gave you guys a frequency, right? Are you aware that I've updated the assignment?
Yes, sir, but that was before we realized that we need to be given it. We were trying to figure it out.
My apologies, Mr. Breed. My apologies.
Other than that, it's basic. It's just what the work we've been doing. Question 1 of the first assignment, use Kirchhoff's. It's the easiest.
Beautiful.
And then, yeah.
Yeah, it's not saying too much, obviously. There, Mr. Casimiro, Simkita, and maybe it's Mr. Silva. Anyone else? Mr. Biavanga. And yes, I'm assuming everyone received the scripts, right? Anyone else has any points on the assignments? If not, you can just say no, then we can move on. But obviously, I'm just using this time for us to share, a few tips and tricks. It's a free 10%.
Sir, can you hear me?
Yes, Mr. Matthijs, Johannes Swanepoel. Loud and clear.
Sir, this is not with the project, but on the previous chapter, resonance.
Yes.
I understand that it's a plug and play chapter. I'm just struggling to understand. Sometimes they're asking you the circulating current. Then they use
Okay.
I equals V over R. And then other times I'm just trying to see here. They're looking for what's the other one?
Personally, I'm just touching the assignment, but I'm not sure
Zimkita,
which group I am
Zimkita,
in.
just hold on. Someone was, okay. Okay, Mr. Swanepoel, what's best? Just send me a WhatsApp, then we can sort that out. Is that fine?
100%. Thank you, sir.
Okay, we'll sort that out. Okay, Zimkita, go for it. Hello, Zimkita. Now she's reconnecting now. Yeah, okay. But yeah, you'll sort out the resonance. Do not worry about that. You'll figure it out. Don't have too much worry. I'm not sure which group I'm in. Okay, there you are, Zimgita. You have to select your group. So some students have gathered 3 or 4, 5 students, and they just selected a group. And then I'll tell you which groups are taken, basically. So you decide on which group, basically. And I didn't want to allocate, what's the word I'm looking for? So you must decide who you're going to partner with and choose a particular group. I think A and F is taken, if I recall correctly. Yeah. So you have to decide on that. Is that clear? Yeah, makes sense. Okay. But I mean, I recommend getting it done as soon as possible. It's really not a difficult assignment, I think. You just want to kind of get it done. And obviously, when we're within a group, you can split the work. Any tips, Mr. Breed, on splitting the work? Or did you do everything, which I think you did? Then we can start the lecture. No tips, Mr. Breed? Family secrets? Do what you're comfortable with. Fantastic. Okay. Anything want to add, Mr. Casimiro, Mr. Zinzo, Mr. Kitonga, before we move on? Okay. Fantastic. Well, I did ask you guys. And yeah. All right. So let's begin. Oh, just one more there. Oh, so far so good. Okay. So guys, when we started, was this guy over here, single phase generator, right? We established that it creates a sinusoidal waveform, right? Obviously, we've done so much analysis. You've grown up, done some inductors and capacitance. You learned about the resonance. But now, that was all in the single phase realm, right? Single phase meaning one coil rotating and giving us an AC voltage. We looked at AC, DC. And now we're taking our AC to the next level. Okay, so this is from John Bird. And yeah, it's just a basic explanation of we have two magnets, we got a coil rotating, and it produces that waveform. However, what we're going to be looking at, oh yes, so I want to just mention something. So the state there is that most consumers are fed by single phase, and what we mean consumers, and this is now on board, no, not on board, on land before I get on board, is you essentially, when you plug in your laptop into the socket, that's a single phase supplies typically, right? You're getting single phase AC power from your wall socket. On board as well, all your basic loads is single phase, right? So you know, I don't know if maybe you can help me. I don't know if you guys have your basic loads or your consumer loads basically is all AC. And they typically are 2 wires, well, 3 maybe. You have a live wire, and you have neutral as well. And obviously that particular voltage is around 230 to 40 volts, right? Yeah. So that's your basic single phase. Obviously your load is sometimes DC, and your adapters would have things like rectification devices to convert the AC to DC, which obviously we don't cover, but obviously just to make you aware. So a single phase essentially has its limitations, and I was thinking of starting lecture, you know, I think maybe make it interesting talking about single phase, the limitation, but I don't want to extend the whole lecture on how 3-phase got born. But what is 3-phase essentially? 3-phase is basically 3 single phases, obviously, but the coils are placed 120 degrees apart, or displaced 120 degrees apart. So we have 3 different coils spinning within the same magnetic field at 120 degrees. And what you're going to get is that waveform over there at B. So you get 3 different voltages. So over time, arguably at certain parts, it looks like you could actually draw like a straight line and say it gives you a constant voltage or EMF. So just start off at just 3 coils displaced 120 degrees apart. Okay. So what it looks like is something like that. So there's 3 waveforms. Okay, typically, okay, there's 3 phases: the red, blue, red, green, blue. We have different rotations. And as the rotor is turning, it's cutting the electromagnetics, and you get this. This is typically obviously produced by an alternator, as we call it. You guys call it generator, but it's an alternator, and we're talking about AC, which we will do analysis on the next level. But it produces this 3 waveforms 120 degrees out of phase from each other. Yeah. So why 3 different waveforms? Let's see. Okay, so I did mention this. This was, I remember when I introduced AC, is that this is what a typical grid looks like. It's very basic level. We generate 3-phase power. Obviously, it's an alternator. We step it up with the transformer, and you'll see it's also 3-phase, and it goes through these high voltage transmission lines, and then it comes down. Then we eventually step down. But what's important to note is that all the equipment of 3-phase equipment, and obviously when we're talking about how to configure the 3 phases, there's different ways to configure the 3 phases. Lastly, once you step it down, we eventually get where you see the Tesla so-called fluorescent lamp is basically where we step it down further to your single phase. So ESCOM or if whatever they are generating or not generating, they're actually producing 3-phase power to the power station, and all eventually gets stepped down, gets stepped up when they transmit it, and gets stepped down to various voltage for various industries. And I didn't mention, obviously, you get some factories running on 3-phase, obviously. On board a ship, your diesel gens will produce 3-phase at a 3-phase power, some voltages. And if you can look at the diagram, you'll see there's this triangle and this Y. And at that particular parts, that's your transformer. And what we have over there is obviously that's a step down transformer, and it steps down the voltage from 6.6 kilovolts to 440. And then sometimes it further gets stepped down to maybe 220, as you can see at that substation over there. So we've got a few, setups over here, and obviously this is on board on what it looks like. We even have I think that's your propulsion, and how they connected in star, azimuths and things like that, bow thrusters and all of that. I think I've mentioned this, basically here, but we'll talk about this. But then again, there's different voltages and stuff. We 3-phase will produce high voltage, so I'll probably get back to the slide. So Yeah, so so I found this actually quite cool. I don't know if I was just thinking of how I can actually show you different supplies and stuff. I was literally put up a whole page with different frequencies. But what we typically have is for single phase around 220 to 240. That's I think that originates from Europe. And then our three phase voltages will range from 380 to 415 at 50 hertz. That's obviously the predominant form of electrical generation or voltage and frequency. If you have a look at our famous America over there in green, we have 100 volts and 120 volts at 60 hertz, and then the three-phase voltages are only at 170 to 20 volts. Does anyone perhaps know why did America go for the 60 hertz, not for the 50 hertz in terms of generation? Does anyone have an idea? And secondly, who has experience with different, frequency and maybe with three phase and different frequencies and things like that? I'm quite curious to hear. Anyone know why they chose 60 hertz? I don't know. Mr. Garcia, higher RPM, maybe, I don't know. I'm not sure. It's an open question. I mean, I don't have a concrete answer myself. Yeah, it is positively a higher RPM because the frequency you see it in motors and stuff. Just opening the discussion where your brain's tired. I can just move on.
Is it because of the affluences they use or something like that?
So again, I missed that, Mr. Casimiro?
Yes. Is it because of the affluences, the type of the equipment they
Yes.
use?
Sure, definitely. That could be one. Has anyone sold on a 60 hertz? Well, typically you have like a 440 60 hertz chip. Who sold on both frequencies basically? I'm just want to hear some experience here. Who's, I don't know. I have, okay. But beautiful, Zimkita, please educate us. Please, please, please.
I'm not sure if my audio is gonna be okay or if everybody's gonna hear me clearly, but I have sailed on both
We heard you for a second. Yeah, you're breaking up, Zimkita.
the refrigeration or
Okay, go back. Can you please start again?
I'm breaking, ne?
Yeah, but then you're back now.
Okay, go back. Okay, so I was saying that I have it's fine now.
It's fine. We can hear you.
Okay, so I was saying I have sailed on vessels that were using, in fact, I have experience on 50 heads and 60 heads. So in my experience, the 50 heads, we used it on reefer whenever we had the reefer containers. The reefer containers were on 50 heads. So we would have a frequency converter. Then we would use that to supply the 50 volts, the 50 heads, 380 volts for the containers. And then on board, we would be using 60 heads 440.
Mr. Ndembani, thank you very much. That's a very, 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 very good example. I really appreciate that. And now you've actually reminded me of frequency converters as well. It's thank you so much for that, for your experience. And I want to say that as an engineer, obviously when you're on board a particular shop and you're expecting a particular frequency, one must be cognizant of what the generation is actually giving. So, and obviously now there's an intervention where we have to use frequency converters to get the correct frequency and so forth. So thank you very much, Mkita. And we do look at some basic calculations in just let me just actually look at a test paper which for electrodes 3. I'm just I'll show you now exactly what I mean. It was one exam. It's an exam. I think it was an exam. 2021. Yeah, we are actually, we are actually had something similar to that. Yeah, I'll just quickly share it. And we actually cover that, in quite nicely in electrodes. But you've really opened my mind. Thank you for that, for sharing that particular thing now, because I've got something fantastic to put in one of my tests next semester. But like, this a perfect three-phase question. Came in one of the exams, and let me just get this back again, where we have different loads connected in different star and delta we talk about. And then if you look at the last part, it says the container ship has arrived at port, and second engineer decides the motor C must be used to power the crane. And what has happened, they have basically changed the voltage and frequency. So initially it was at 415 and 50 hertz, and then we've got 317, and then obviously when it's at port, it's going to be used to power 360 hertz. Obviously this was like a theoretical example, but yeah, it's something similar to that. And obviously we have to use a frequency converter over here, thanks to Zimkita, that to get this correct. So yeah, that's just a case of a question which is next semester, which I typically look at. But we will look at a bit of it now, obviously. Okay, so like I said, not going to the stories, but just going to, I've got a list of like a lot of reasons why we have advantages of a three-phase system. I'll just probably take out a few of them, which I think is worth looking at. But obviously you have the slides, excuse me, and you can obviously refer to them. Cool. So one of the reasons is to transmit a specific power over a specific distance at a given voltage. What is important there, a three-phase system needs less conductor material than a single phase. So that's fantastic. We have less copper, and obviously that's more economical and more cheaper. And a nice one is a size of a three-phase system operated machine is less than the machine operated a single phase. So typically a three-phase would be more compact and you can get more voltage. Obviously, we'll figure that out why. Versus a single-phase machine, that's one case. A three-phase system has a less voltage drop from source to the load points, and this is kind of one of the two things that's important. The next three things important. There's a uniform rotating magnetic field, and that's essentially to do with these voltage waveforms as well. Like I said, it's nearly constant, but anyway, we'll talk about that. And again, let's say three-phase motors are simple in construction. Yeah, yes, we'll talk about that. Polyphase system produces power at a constant rate. That's what I meant, constant voltage, obviously. And also with three phases, we can transmit more power. And one of the reasons why, obviously, is because of the configurations, but we can get more voltages. I mean, if you look at compare the two voltages, single phase around 200, three phase obviously can generate more voltage. I mean, you kind of think about it, the laws of electromagnetic induction, you have more conductors, bigger running, bigger magnetic field, we get a higher voltage essentially. There's more, the three-phase machines are more efficient, compared to single phase. Furthermore, your three-phase systems they typically smooth and vibration free. Which you compare to your diesel, your petrol gens, your single phase, they typically are more noisy and have higher vibrations. Yeah, that's one of the other important ones is that a single phase supply can be obtained from a three-phase supply. So that meaning that if you have a three-phase supply, we'll talk about that obviously as well. You can actually run if you have a three-phase supply, you can run a single phase on there, right? Going from the line to the neutral. And they're saying that a three-phase supply can be easily converted to a single-phase supply. Obviously, I did mention that, but it's harder to convert a single phase to a three-phase. The last few, but this is typically with electrical machines or equipment, particularly transformers, alternators, and motors. The three-phase motor can give you a uniform torque. With a single phase, will give you a more pulsating or it kind of you know, the waveform, the sinusoidal waveform kind of gives that kind of torque. It's quite interesting as well. Obviously, we heard about single phasing. I'm hoping in three-phase motors. And in that case, the motor can still run in the three-phase setting, but if it was in the single-phase setting, yeah, that's not going to happen. And then lastly, I think right at the end, I would like to make a special point there that also three-phase motors have better power factors than single-phase motors. So there's a lot of benefits as to why we use three-phase systems. But the key things are it gives you more power, which is the one. We need more power for big equipment. It's more efficient, meaning better power factor, obviously. It's also more uses less conductors. That saves a lot of money, obviously. It's smaller in size, and obviously it can give us two voltage sources or two different types of voltage for whatever application. That's just encapsulating everything. Okay, so we've talked about three-phase. Now it's just three wires, 120 degrees out of phase, spinning in the magnetic field, and you get some voltages, right? But the question is, how do we configure them? And obviously, we've talked about very briefly, it's a two-wire system or maybe three-wire system for AC. But then, I mean, two wires, one with the red and the black, and obviously you have your green one going for your ground. And it's fairly simple to imagine if you've seen a plug before. But how do we configure this three-phase supply? So obviously, I would like to hear you guys. What is your experience with configuring? And obviously, we know, actually, you guys didn't cover it already, your star and delta. So I just want to open anyone about star and delta configurations. Any experience with it? And obviously, I'll talk to the maths and what we need to do. Any experience with star and delta with the three-phase configurations? Zimkita, do you have any experience? Mr. Priyat, Sasha? Okay, doesn't seem like anyone has. That's fine. Okay, so we're looking at two configurations, and one of the first ones is called the star connection. So basically, what it means is we're just configuring the wires in a particular way to get a particular outcome. So the star connection, I also think it's called the Y. It's also called Y in other terms, and we configure the wires and there's a common neutral point. So if you look at the diagram over there, they use RV. Oh, someone's
Well, my
yes.
experience with Star Delta is we normally use it on motors, and the main reason we use Star and Delta is so we can reduce the amount of current that is drawn when the motor starts. So instead of using auto transformer, for example, then we use the Star. In that
Yeah, we've just lost it there, but yes, that's one of the applications. They star and delta. I'm starting for motors, and yeah. Oh, Zimkita, are you back again? You in and out. Are you back now? Can you please continue? Star and delta starters. Okay. Let's just give it a minute and then. Yeah.
Yes, I lost my signal there for a second. So I was saying with Star Delta, we used it mostly on motors, especially big motors. So the main reason we use them is so that we can reduce the amount of current that it draws when it starts up. Because if you just use it as an auto transformer, for example, when it starts up, then it would consume so much
Because you cut off there, yes. Use more current. Yes, that's correct. Because in Kita, well, let's thank you for that. Anyway, she's reconnecting again. Okay, so the first one is star. And what's important to note over there, we configure 3, and there's a common, it's configured to a common neutral point in the center. And there are 2 terminologies you have to be aware of. So there is a line voltage, which is measured from A to B there, if you can see on the diagram. And then the other one would be phase, would be from line to neutral, from that center point, the neutral point to at the NA. So what's important to note is there are 2 different voltages or currents. One would be the line current between the 2 points there, A and B, or R and Y, which would be called your line, and then from A to N, which is on the line to the neutral, which is also called phase, right? Phase voltage, phase current corresponds to each other. We'll talk about that. So as I mentioned to you, the system is balanced, meaning that the phases are equal, the impedance of the phases. We have equal current flowing through them, right? So kind of self-explanatory. Therefore, we have 3 voltages, which are equal in magnitude in each coil, basically, or each load there, right? They're all 120 degrees out of phase from each other. Cool. So then what we basically do is take the resultant, we take essentially the vector difference between the 2. So we just, not that we have to do this, and then we basically, what we do, we find the, because in Kita, you're back, we moved on. So, but yeah, I'll talk about star and delta starters again. Right, and we in essence find the sum of these vector differences, and obviously you're seeing a few lines there, and you can see on the right there, we take, if you look on the diagram over there, you've got the E and Y squared plus E and R, and we basically take the resultant of that phasor diagram, and then we end up with a nice simple formula there, where we have okay, so yeah, anyway, you have your phase voltages there, and that equates to the line, and in essence we get this relationship where the line voltage is equal to √3 times the phase voltage. Yeah, so if you want to see the maths here, if you are interested, there's load shedding. It's fine, it's a pain, I know. At least I have the recorded, yes, it's fine. So long story short, yeah, just applying the maths, getting phase differences between 2 lines, we get a relationship over here. And we find in the star connection that your line voltage is equal to √3 times the phase voltage. Once again, your phase voltage is, it's the line to the neutral. So from line to line, we have a voltage of, let's say, 380 volts. And then if we divide that by √3, you get a particular phase voltage of 219.393. And obviously that talks that 2 voltages I was referring to. So yeah, furthermore, that's your voltage, your line voltage and phase voltage. However, the relation between the current and the voltage, or the line current and the phase current, we all know that there's 3 currents flowing through the star connection of the same magnitude. And in essence, we find that the line current is equal to the phase current. And yes, so that's one, that's important. So your phase voltage is your times √3 gives you a line voltage, and for your phase current is equal to your line current. That's for star connection. Cool. This is now just a quick explanation of what it looks like. What I like is showing the voltages. So from load 1, which is essentially on the phase, you get 230 volts. And if you times that 230 volts there by √3, you'll get your line voltage of around 440, which I'm finding quite strange the way it looks. Oh no, there's 2 different loads, 2 different voltages, but the idea is that the star gives 2 different voltages, 230 and 440. I'm not sure, it doesn't really look right on the calculator. Anyway, yeah, I don't know, strange. Yeah. Okay, cool. And I'll make a special note there that it's typically used for long distance transmission, but you'll talk about that. Yeah. So the way I think of the star connection in brief form is I think of it as a series connection where your line current and phase current is the same, and your voltages obviously it's different, but obviously it's a factor of √3. And if you're wondering where the √3 comes from, it just basically comes from the vector sum of the phases and stuff like that. Yeah. Cool. Next, I'm just summarizing the star connection. Line voltage are 3 times the phase voltage. Line currents are equal to the phase currents. Line voltage 120 degrees apart. Line voltage are 30 degrees ahead of the phase voltages, and that's something important. Maybe if you do 3-phase circuits, we'll talk about the other stuff here. So that's just important to note. Line voltage and the phase line voltage and the phase voltage and the line current and the phase current. Another type of connection is delta. So delta, we have three conductors and we assemble it in a triangle. It's also called a mesh connection. And they're saying the finished terminal of one winding is connected to the start of another. So that's another way of configuring a 3-phase system. And talking to this, our phase voltage, looking at, so in this case, what our phase voltage is will be, for instance, between 1 and 2, or 2 and 3, and 1 and 3. That'll be a phase. Our voltage, it's basically, it's one side of a triangle, that'll be a phase, and then your line voltage will be from point 1 to point 2, or 1 to 3, right? Again, I'm going to say this, I think of this as a parallel arrangement, therefore the voltage will be the same across all phases. Conversely, especially if you compare that to the star connection. So again, we're going to be looking at the relationship between your phase voltage and your line voltage over here. In this case, not going too long, your delta connection, your line voltage equal to your phase voltage. So that is essentially the opposite of your star connection. And then basically looking at your currents now, we do exactly the same kind of math, but then you apply Kirchhoff's law at junction 1, and which is basically at the center over there where your resultant current and your current's going in because your current's going out. Find the vector difference and then do the resultant thing again, and you'll end up with also another √3. Because another √3, and you find that your line current is equal to √3 times the phase current. That's what it basically is over here. And then comparing the two, not comparing the two yet. So for your delta connected system, the line voltage are equal to your phase voltages. Your line currents are 3 times your phase currents. They're also 120 degrees apart, which is still the same. And the line currents are 30 degrees behind and not ahead your thing. And that's important when you do your circuit itself. And then luckily at the end of it, we just have 2 comparisons between the two. And obviously we have some examples. I'll talk about some applications and we'll do some examples. There's a lot to talk about. Star connected, similar ends are connected together. The similar ends are connected in the delta system. But the main 2 important parts I want you to know is that for your phase voltage, that's going to be √3 times your phase voltage is, or your line voltage equal to √3 times your phase voltage. And then on the delta side, we have the same. Your line voltage equal to your phase voltage, and on your current side, for the star side, your phase current is equal to your line current, and on your delta side, your line current is equal to √3 times the phase current. Your star connected system typically is a 4-wire arrangement because you have that central point and neutral point, and whereas your delta is 3 wires and there's no neutral wire available. I just want to make you, someone told me like a short way of remembering. Typically for star systems, it's used for supplying supplying, and then whereas your delta system is for running on load. And what I mean is that your alternators are typically or in star. So especially when you're supplying current, right? You want to have it typically in a star arrangement. But when you want to run on load, so when you're actually running motors and specifically motors to get more voltage or more power connected in delta, hence the star and delta configuration we talked about. Okay, so I said a mouthful over there. And yes, I've just got some data plates for you on various equipments, and I think I'll just quickly just duplicate that slide, and I just wanted to show you. I did mention this to you before, and just like look at a few. No, let's just delete these two, for instance. But if you look on the nameplate or data plate of the stuff, so this is of a motor, and you can literally see over there. If you run that motor on star at 50 hertz, it will give you 37 kilowatts, and gives you the that's your line voltage. Then it gives you a power factor. You can actually work out. What you call it, that power there. Hopefully we can do that. And if you connect it at star at 400 volts at 50 hertz, still gives you the same power. Obviously it'll draw less amps, and as you can see there, obviously we have sorry, it draws more amps actually at that particular power factor. Another configuration, 380 at delta, draws 72 amps. Obviously there's a higher voltage there, same power as well, different power factor. Then if you configure that in star at 60 hertz, as you can see, it's quite all over. It's another motor nameplate. Let's look at this. Look at the asynchronous generator. Quite strange. Just can make that smaller now. You can even see over here we have some delta star connection. Yeah. State and rotor volts as an example. And over here, let me just remove these ones now. Okay, I've got two transformers over here, and here we talk about how we connect the different windings. The primary side and the secondary side. Obviously, we'll touch on that when we do transformers. The primary side is connected in star, as you can see there. I'm sorry, in delta, then star. And similarly on the high voltage side, we have a delta, and then across on the other side. And these configurations will tell you, whether it's a step down or step up transformer. So that's also important. Once again, you can see it's all there. These things are not in the theoretical domain. It's real life application stuff. As Dr. Tembani has said there, one of the applications which I thought just mentioning to you, and obviously you guys are aware of these things. One of the methods of starting a induction motor is using a star and delta starter, and what it does is that you start the motor in star. You can actually, I don't know if you ever heard the changeover. That's what it looks like. The voltage across each winding is a lot less. It takes, and then basically, and then obviously it's √3 less than the voltage, the full line voltage. So what they say there, so at the time of start connection of the motor made in a star fashion, so that the reduced voltage is applied across the winding. After the motor attains speed, the same windings through a changeover are connected in delta. Obviously that is done through contactors. I think you guys are aware of that. And they're saying the starter is provided with overload and under voltage protection. Obviously, in the case of we don't want that to happen. And there are three common methods, and that would be a direct online starting, your star and delta, and your auto transformer methods, the predominant methods. And this is typically used for motors up to 25 horsepower. I'm not sure exactly in how much watts that is. And yeah, anyway, so that's one application of star and delta. Another one would be the transformers again, which is also important. And we can configure the transformer in 4 different ways. I just put some pictures of a single phase transformer and a three phase, and you get different types. You get a shell and you get your core types, which I'll briefly discuss in that chapter. But what's interesting, if you look at the Y or star connection, that's typically used for a small current and a high voltage. If you go for delta, you're looking for large currents and low voltages. So obviously you can see one's like a step up, one's like a current transformer, one's like a voltage transformer, things like that. You've also got your delta Y, which is very, very common, which is a step up transformer at generating station. So that's the one typically after the generator or the alternator at the power station. Then you also have your Y delta, which is a step down, which is typically at the end. And you can obviously see at a step up, because your line voltage, you get the phase voltage, you expect a high voltage, and then you drop the current and having star, so that you have a low current going through the wires when transmitting, so we can get less I square R losses, or less heat. And conversely, it's the other way around. But anyway, we'll talk about that. So this is an explanation of how it's configured. Yeah, so there's a typical setup on obviously on land, and also on board with something similar, but on a smaller scale. Alternators connected in star. Goes to a step-up transform, which is a star delta, steps up the voltage, low current, high voltage, that gets transmitted, and then what happens is it steps down again, and delta star, or the primary side, secondary side, then go delta star, and then basically there, once you have the substation, the house, the factories will typically connect on 3 phases, whereas the houses will connect on single phases. And obviously, while the factory can get both types of voltage, your single phase and 3 phase. I am aware, if you look at a tariff, tariffs, some houses are connected in 3 phase and you will get billed higher. So please check your bill on your tariff structures. That you could be on a plan where you're on a 3-phase plan. But some people run factories at home, so have a look at that. And anyway, so that's some applications of star and delta. And then the last part of the lecturing part, I've been talking so long, is that we obviously want to work out watts. As engineers, we want to know watts. What is the actual language we speak? And to basically find the power, it's basically going to be it's still your I squared R, or I times V, and we work per phase, so it'll be 3 times each phase, which will be 3 times your I phase squared times R. And obviously R is not just R, it's actually a Z, but obviously you can use R, the R part, which is the watt part of it, and that will give you the power consumed in one phase. But obviously we don't want to work with phase voltages, because we typically measure line ones a lot easy. And in essence, your final formula for star and a delta connection, if you look right at the bottom, will be √3 times your V line times your I line times cos of theta, which is your power factor. Alternatively, you can use 3 times I phase squared times your R phase squared. That'll give you the watt counterpart. Furthermore, to find your apparent power, or the actual electrical power provided by the supply, or whatever the connection, it'll be √3 VLIL. So obviously the important thing is one value, and let's just quickly get it, just to be fancy. Let me just type it in here. Google √3, square √3, sorry. 1.73. Just give me a moment. Yeah, I just wanna emphasize it. That's that kind of thing I'm trying to do. Let's just stop this over here, and yeah, that number is now introduced. So it's exactly the same as your single phase stuff, but it's now incorporated. Oh, sorry. It's incorporated into your power formulas. And your power is traditionally VI cos. Now it's √3. It's just a basic √3. And then, yeah, there's some comparisons again between star and delta. You can have a look at that yourself. I think I mentioned a few, but just some key factors there. The speed of delta motors are high because there's a bigger line voltage. Star motors will be slower, the speed. Star connection, you require less turns because of the voltage. Low insulation is required on the star side, and then heavy insulation on the delta side. And then in power transmission, star, like I said, to transmit power, to supply power, you typically use star. And then to run things on load or power distribution in industries, you always want to connect things in delta. Right? That's the main points. Okay, guys, finally we can start doing examples. Are there any questions? Any comments you want to make before we actually start solving examples? Was it clear? Did I lose you? Was it interesting? Was there anything you want to add maybe? Yeah, I know it's a mouthful, but I just wanted to explain it well. Put a bit of detail here and there. Okay. So let's do the first example. Right? And then we can we have some examples to do here. We can do these two and maybe maybe two more, and then I'll just talk about power factor correction and then we're done. So I've just literally put a lot of the lecture in front with a small power factor correction, which is you're familiar with. So we can look at it's now just basically the tutorial part of the lecture in terms of starting output. So let's do the first example. You can try the second one, and then we'll see. Okay, so let me just get my whiteboard ready. Oh, I'm just paste that question. I want to just make this right again. So root 3 is a new guy, and I want to paste it in the start of the slide here. Cool. And yeah, I'm gonna try to do some basic real life calculations on stuff. You'll see. See if I can get it right, but just let's start on the first example. Cool. So example 9.1, you can follow it in the textbook if you like. I'm just gonna paste him, and then we'll start with cool. Why? Oh, there we go. It's a bit of a lag on my side there. Okay, so let's do the first one. Let's see if you guys can see it. Yep, nice. Just lock it. There is a lock. Cool. So example 9.1, and let's begin. So we have a three-phase motor. It has an output of 32 kilowatts, an efficiency of 83%. And what that tells us, we need to find power in. And what they're asking for is, and it's applied with 355 volts and at a power factor of 0.85, right? And we need to calculate the line current, phase current, that's connected in delta, and then also the phase voltage was connected in star. Okay. So yeah, we'll be solving a few problems. I'm just looking for my book. Okay, don't actually need my book. Okay, so first thing is first, right? So it's connected in star. Oh, just give me a moment. Oh, the pin is not activated. Yeah, it's activated now. See, so it's connected in delta. No, man. Okay, and that's your motor. You've got the line voltage is 335 volts, right? And yeah, okay, there's a few characteristics which I'm not going to really worry, but the idea is to first find the line current. So as you learned, your new formula for P in will be VL IL cos of this. And what we need to find is this guy over here, right? But obviously we have the output of the motor. So what's the official symbol for a motor? I don't know if anyone knows. So we know that on this, it looks like a suite. You know, at the outside part, we have 32 kilowatts. So that's the power is providing, but obviously through here, we need to, over here, we need to, we need to get how much electrical power to throw in. So that's going to be P in. So obviously your P in will just be P out divided by your efficiency. Can someone just give me that P in? Thank you. But yeah, can you, and sorry, yeah, just someone get the P in and take, I'm not sure if you guys had your notebooks out, but yeah. Let's get P in quickly. All right, so that's around 38. It obviously should be way higher. Not way higher, but I mean, you know, should be higher than your it's around 38.554, right? Yeah, let's just call it 38.55. Yeah. 38.554 kilowatts. Right, decent amount of power. Just wanna, okay. So now what you have to do is find the line current, right? So when you're dealing with delta, I typically always write this out, don't have to anymore, but we know that your line current equals your line voltage equals your phase voltage, whereas your line voltage is equal to your line current is equal to √3 times your phase current. So in this case, so you just have to substitute over here. So it's 554 times 10 power 3. That's √3 times that's 335. So I just want to make you aware, typically line voltage is given unless stated otherwise. So typically your line voltage will be given. That's what we can actually measure. Times your power factor 0.85. And obviously times your line current. So if you're going to solve this, let's find your line current. I encourage you to do that. That'll be your line current over there. So what did you guys get? 78.1 should be 17. Yeah, 78.17. I'm happy with that. Right. 17 amps. Cool. So again, this is the line current. So now what they're asking for is the phase. Now that's A. So at part B, they want the phase current, and the phase current for a delta configured system is I line equals √3 times I phase. Therefore, I phase will be equal to I line divided by √3. This will become super easy for you after some time. So let's just quickly get to line current, 78.17 divided by √3. What do we get? That should be easy. 45.13, I'll take that, yes, 45.13 amps. And that's correct. Probably get 2 marks for a question like this. Now they want the phase voltage if the motor is connected in star, and that's quite simple. If it's now connected in star, remember your phase your star, your line current is equal to 3 times that. And like I said, there's a star connection, so the current's the same, and you know that your line current is equal to your phase current. In this case, all you have to do is take your phase your again, line current equals √3 times VP, subscript P, the phase. Take the 335 divided by √3. And let's get our phase voltage. Done. Well, that's just a warm-up anyway. And what do we get? 193.412. So as you can see, volts. Yeah. So that's a nice basic introduction to what this is about. Let me give you another one. So we're just going to be solving a lot of these problems over here. Let's see if you're competent for this here. Okay. Move along. Paste another one. So this is problem 7 in your John Bird textbook. Recommend you check that out. And over here, what we have is what are they asking here? So we have 3 coils having a resistance of 3 ohms and inductive reactance of 4, and are connected in 1 star and 2 in delta. And basically, for each connection, you must calculate your phase current and your phase current and your line current. So number 1, in delta, and your line voltage is for 15 volts. Number 2, we've got star, and the line voltage is also for 15. Okay, so that means each phase, what they're saying here, just as an illustration, that is your resistance and that is your inductor. Obviously, it represents the same thing. And here we have 4 ohms, and the other guy is, sorry, that's 3 ohms. 3 ohms, and the inductor is 4 ohms. Cool. So how do we calculate current? In a AC circuit? Who can tell me? Who still remembers? You guys forgot. So V, let's do this. V equals I Z. Now to make you aware here, when we typically do this, this thing, we always work per phase. Always per phase when working with Z, right? Or because you're given your impedance per phase, so you have to work with your phase voltage, your phase current, and obviously your phase or whatever. Is it clear to everyone? Is it clear to everyone when you work with the windings? Yeah, thank you, Zingita. You always have to work per phase. So what it means is that, yeah, anyway, you'll see what I mean. I'm just going to do the first one. So we know for a delta connection, your line voltage is equal to your phase voltage. Therefore, we can say 415 at 0 degrees. All right, That's typically what we want to do. And our Z phase is going to be 3 plus J4. Luckily, it's given to us. And then we can find our current in our phase over there, right? So remember the one to the line, the line voltage and the line voltage and line in phase voltage and the phase in line currents. So let's work out the phase current here for this. Obviously that's in complex numbers, and then I'll have V line here, V phase, and then we'll have I line and I phase. Okay, so let's work it out. I line is 83 degrees at 83. 83 at minus 53 degrees. Fantastic. Yes. What is this, my students? What is this, guy? What is this?
It's lagging, says.
Not your phase angle, but what is your phase angle? It's fine, your phase angle lagging, good, but what does it also represent? Power factor. Well done, Mr. Kitongo. It is a power factor, my students. So if I had to ask you what is a power factor, you guys remember, the power factor will be cos of this, cos 53 degrees. And cos of 53 degrees is 0.6, would be 0.6 lagging. I'm just throwing that in there so that you can't, you always stay, yeah, there we go, fantastic. So we've calculated this, so let's talk. So for delta connection, we have a the line voltage. Line voltage is 415 volts, and your 415 volts, and your phase voltage is also 415 volts, right? We know this. Your phase current is 83 amps, right? And what will be your line current? Is 83 amps as well? Can someone please give me a line current? Anyone? Mr. Sima? Yes. It's basically times root 3, and it would be 143.76. I'm deliberately not including the angle because the angle is the same, the power factor. 143.76 amps. Obviously, this is your phase times root 3. Cool. And you can compare the values there, you know, draws more current, less current. Interesting. Okay, so what I want you guys to do now is do the second part. Over here. You can do the second part. So it's connected in star. VL is 415 volts, and your Z phase is also 3 plus J4 ohms. Okay. So yeah, okay, well, should have choose a better spot here, but anyway. So yeah, go ahead. I'll give you guys around 2 minutes to quickly do this. Then I'll just do the critical parts. Yeah. Yes, line voltage. That's not the line voltage. It can that's not correct. The line voltage is still 415. So I don't know what exactly you're saying there. The line voltage remains the same. You have to work out your phase voltage. There we go. Okay, someone has done it already. And let's quickly do this. Then we go on our small tea break, and then we can do 2 or 3 examples. And yeah, we can close off early today. Nice. Let's see. Yeah, so for a star system, our line voltage is the √3 times the phase voltage. So the first thing would obviously be, say, 415 divided by √3, and we can get our phase voltage. And once we do that, that's 415 divided by √3. We get an answer of 239.6 volts, right? So we have a phase and a line current that's sorted out. Sorry, our phase voltage and line voltage, but what about a current? Once again, with the impedance, you have to say your phase voltage over your phase current and your impedance. So your phase voltage is 239.6 at 0 degrees, and then your impedance will be 3 plus J4. And we can call that divided by I phase, and 239 at 0 degrees, 3 plus I times 4, and you should get an answer of 47.92, also that is minus 53.13. And what is my line voltage, Mr. Kitongo? Mr. Duplessis, are you okay there? What is my line current, sorry? That's incorrect. That's not correct. What is my line current, Mr. Silva? Yeah, that's 47.92. Thank you very much. So we know that for a star system, 47.92. Star system, I phase equals I line. Straightforward. Okay. All right, guys. That's the first 2 examples. I'll probably plan to do one more and change it up. But let's go on a tea break for say 10 to 15 minutes, and then we'll continue with a nice example. I'm going to change this one up a bit. Example number 3. I'll put in a few nice ones. Maybe I can do one more of this. Then we're just going to go into power factor correction, and then we're basically done. I won't spend too much time. I mean, I can literally close the lecture early. I'll be done before 3. But let's take a quick tea break so we can renew our minds for the next problem. Okay, this is the end of session 1, and then you can continue session 2, let's say 5 minutes past 2. Okay, guys. See you then.